Greetings, ladies and gentlemen. In this video, we will go over how to solve first-order differential equations. And, well, just one method of solving first-order differential equations is separation of variables. Now, separation of variables is perhaps one of the easiest methods when it comes to solving a differential equation. Now, before we get into that, what does it mean to solve a differential equation? Well, a differential equation in theory, is simply a derivative. We want to go back from a derivative to an original function. Okay, so in order to do that, just from calculus, we know that we have to take some sort of integrals. All right, and when we do take integrals, we always get a plus c term. Now, in differential equations, an equation that has a plus c term is called a general solution to the differential equation. So there's a general solution, and there's also a particular solution. Now, a particular solution is when we have an initial value condition, and that initial value condition tells us exactly which curve we're looking for. It eliminates the c, in other words. Okay, so number one here, let's jump straight into the problem. Number one has an initial value condition. Okay, so we'll call this an IVP. Now, separation of variables essentially says that you want to take all of the y's and move it with the dy term, and take all of the x's and move them with the dx term. Now, number one doesn't seem to have a dx term. Well, it actually does. It's built into the y prime. Let's rewrite it. So just come over here. Number one says y prime is equal to x squared divided by y. We can rewrite this as dy dx is equal to x squared divided by y. Now, the idea of these equations, like for separation of variables, is to move the y with the dy term, x's with the dx term. Okay. Now, let's just multiply the y onto both sides, thus eliminating the y from over here, getting y dy divided by dx is equal to x squared. Let's multiply the dx on both sides so that we can eliminate the dx from the left and get on the right. Therefore, simplifying down into y dy is equal to x squared dx. Now, here's what I mentioned about the integral. To get rid of a differential, or a dy or dx, you would simply want to take the integral of that piece. So you would take the integral of the left and the integral of the right, thus getting, by the power rule of integration, y squared over 2 is equal to x cubed over 3 plus c. Now, you might be wondering why I don't have a plus c on this side. Well, by convention, we usually want the plus c's to be with the x's. Now, just say if we had put a plus c on this side, well, c is just an arbitrary constant. We don't know what that constant is. If the constant's on the left side, it doesn't necessarily have to equal to this constant here. So in other words, if we add or subtract that constant to the right, we would still end up with a constant on the right. Okay? So that's why we skip a step and we just go over here. Now, this is already a general solution to the differential equation. A lot of times, though, we're asked to submit these general equations in simplified format. In other words, solve for y. Now, to do that, we would simply multiply the 2 on both sides, getting y squared is equal to 2 times x cubed over 3 plus c. Distribute the 2 inside these parentheses, getting y squared is equal to 2x cubed over 3 plus, well, 2 times c is just a constant. One constant times another. It's just a constant. I'll just write that over here. Now, we can solve for y further by taking the square root. So y is equal to plus or minus the square root of 2/3 x cubed plus c. Both of these are mathematically equivalent, but this one is just the simplified general solution. Now, let's take care of the initial value condition for this problem. Okay, now actually let me just change that a little bit here, where it's actually y of 0 is equal to 1, because y can't ever be 0, since seeing as how it's in the denominator right there. And that would simply be undefined. So what we can do here is substitute the initial value into the problem and solve for c, our constant term. So in other words, we have for y is equal to 1 plus or minus the square root of 2/3, well, x cubed. X is simply 0 from here, 0 cubed plus c. Now, let's square both sides to get rid of the square root. Okay. Thus getting 1 is equal to, now the square would actually get rid of this plus and minus as well. 2/3 times 0 is simply 0. Thus getting c equals to 1. Because c plus 0. And then the square root would simply go away. Now what happens is that we have our particular solution, which when we plug in the c into our general solution, we would end up getting y is equal to plus or minus the square root of 2/3 x cubed plus 1. And this would happen to be our particular solution. Right? Now, let's go back to see what we did. We wanted to use the separation of variables because that's usually our first method of solving these problems. Separate the y's, in other words, put the y's with the dy's, x's with the dx's, and simply integrate. Right. Now, let's go on to number 2. Now, number 2, I actually like this problem quite a bit because it requires a little bit more thinking and manipulation of the algebra before actually solving the problem, before actually being able to use the method of separation of variables. Now let's write this down. Number 2. dy dt is equal to 1 plus t plus y squared plus t y squared. Now, just looking at this, you really can't see a piece that we can divide the y's onto this side and multiply the dt's onto this side so that we can have only y's on one side and dt's on, or t's on the other. Because this y is also attached to t. So let's do a little bit of algebraic manipulation. Therefore, getting dy dt is equal to 1 plus t plus, let's take out a greatest common factor between these two terms. Y squared times 1 plus t. Okay. Now it looks like if we put this in parentheses as well, this is common between both terms. So we can pull that out as a greatest common factor as well. So if we have 1 plus t times, well, that would be 1 plus y squared, simply because I pulled out the 1 plus t, would be equal to dy dt. Now it seems like if I want to, I can move this onto this side and the t's onto the other side and just simply get y's on one side, t's on the other. Okay. Now this would simply end up being, now I'm going to skip the algebra steps and proceed to the next step, dy divided by 1 plus y squared is equal to 1 plus t dt. All right? So this does take care of the problem of separating the variables. Now in this next step, we would simply want to integrate. Now, if you try a method of u substitution, you'll find that it won't really work. This is not suitable for a u substitution problem. However, if you think back to your calculus and your trigonometry, you'll realize that this format fits, that this integral format fits the description for the arctangent. In other words, answer for this piece would be arctangent of y is equal to, I'll take the integral of this, t plus t squared over 2 plus c. Now this is the general solution, but it is not the simplified general solution. So, in other words, we have to solve for y. To solve for y, we have to get rid of this arctangent. Now I'm going to move this up here. To get rid of an arctangent, you would simply combine it or make it a composite with its inverse, or in other words, the tangent function. So the tangent of the arctangent of y would be equal to, now if on the left side we take the tangent, you also have to do it on the right side. That's what equations are. What you do on one side, you do to the other. So you have the tangent of t plus t squared over 2 plus c. This and this would go away, thus coming up with y is equal to tangent of t plus t squared over 2 plus c. Now, this is your simplified general solution. This equation does not have, this problem does not have an initial value condition, therefore we'll stick with this. Now that is separation of variables in a nutshell.